Thank you for attending my talk. I'm going to present joint work with Jakob Bech-Theis Knudsen and Mikkel Thorup. And my name is Anders Åhmann. We're all part of BARC, which is Basic Algorithms Research Copenhagen. And the title of the talk is Load Balancing with Dynamic Set of Balls and Bins. So let me start out by giving you an introduction to the problem. So the goal is to distribute a set of N clients, which we will call balls, into a set of M servers or bins. And I want you to think of this in a hashing style setting where we have a universe of possible ball IDs and a universe of possible bin IDs. And at any given point, we have a fixed set of balls and a fixed set of bins, and we want our hashing style solution to give a distribution of the balls into the bins. And we want our data structure to support insertions and deletions of balls and bins, and also to support ball searches. So that is the dynamic part of the problem. So let me give you some examples of what this data structure should support. For example, if we want to search for this red ball, our solutions will typically have to go through a number of bins until it eventually arrives at the right one. So maybe it would start looking at this orange bin, and then on this green bin where it does find the red ball. We could also imagine asking for the deletion of a ball, and again we would go through a number of bins until we find the bin containing the blue ball, and then we could delete it. We could also but we could also imagine deleting a bin, the green one. And if we were to do this, then these two balls belonging to that bin would have to be reallocated to new bins. Could look like this. And we have a dual goal in mind. First of all, we want to minimize the maximum load, but we also want to minimize the number of bins visited during these updates. And our solution will actually obtain a trade-off between these two objectives that in a certain sense is optimal. So before describing our data structure, let me present some related work. The most important is probably consistent hashing. And the idea behind consistent hashing, it's a data structure for this problem. And the idea is to hash the clients and the servers, or the balls and the bins, to a circle. And what we do is that we forward each ball in clockwise direction to the nearest bin. So the final placement of the balls into the bins could end up looking something like this. And let's take some examples of updates to this data structure. It could be that we want to insert a ball, and in that case, we just hash it to the circle and forward it to the first bin in the clockwise order. An update that's a bit more complicated is inserting a bin, but again we would hash it to the circle. But now this green interval, the balls hashing to that interval actually belongs to the newly inserted bin. So we would have to find those balls in the bin following in the clockwise order and pull these balls back to the right bin. And this is a very popular solution in practice. And in fact, these two papers combined have more than 17,000 citations. So it's widely used. But however, it does have some limitations. And the most important one for us is that when we have M bins, some of them, the normal one would cover a fraction of 1 over M of the circle. But we also expect some of them to cover an interval of length log M divided by M. And these would also get an expectation, a factor of log M too many balls. So in a sense, these bins would end up becoming very overloaded. And one idea to resolve this issue is to introduce so-called virtual bins. So the idea is that actually we don't place the bin on the cycle any longer. We just represent it k times on the cycle. So each bin gets, for some number k virtual bins on the cycle. And when inserting the balls, we hash them to the cycle and we forward them to the first virtual bin, placing the ball in the corresponding actual bin. Could go on like this. This red ball gets put in the orange virtual bin and gets placed in the corresponding actual bin, and so forth. And the idea is that you can think of these virtual bins as covering in counterclockwise order the interval behind them until the next virtual bin. So the blue virtual bins would cover these blue intervals, and the orange ones would cover the orange intervals. And the point is that if we use more virtual bins, we get a more uniform bin cover. So to be more specific, if we used log m by epsilon squared virtual bins per bin, then with high probability, each bin would cover an interval of length 1 plus epsilon times the average with high probability. So this solves this issue of having like a non-uniform bin cover using standard consistent hashing. And when the average load in our M is large, say omega of log M, then it follows from standard probabilistic bounds that if we have this uniform bin cover, then almost uniform bin cover, then all loads will also lie within a 1 plus minus epsilon factor of the average with high probability. However, if we are in the lightly loaded case where, for example, we have the same number of balls and bins, then even with a perfectly uniform bin cover, we will still have that some bins have load at least log n divided by log n, whereas the expected number of balls in a bin is a constant. And that is in fact in the case even just distributing n balls into n bins completely uniformly at random. So we still get some quite heavily loaded bins. And a solution for this problem is the so-called consistent hashing with bounded loads. And the idea is to say that the bins have capacities, and whenever they are full, they start forwarding their balls. So at some point, the setting could look something like this. And when inserting a ball, this orange one, it gets placed in the first non-full bin. So this was easy, but then when we insert this pink ball, the first two bins in clockwise order are full, and we place it in the third bin. And let's say that each bin has capacity which is a factor of 1 plus epsilon times more than the average. Then in this paper, it was proved that in expectation, when inserting a bin, we have to visit order 1 over epsilon squared. Sorry, when inserting a ball, we have to visit an expectation order of 1 over epsilon squared bins. And the paper also proved similar bounds for ball deletions and bin insertions and bin deletions. For the bin insertions and deletions, we have to multiply this bound by a factor of c. And actually, these similar bounds all follows from the theorem above, so it is sufficient to analyze the ball insertions. And at this point, it makes sense to state one of our results of our paper, and that is that we can reduce this to order 1 over epsilon with a new data structure. And this 1 over epsilon is just not any arbitrary function of epsilon. In fact, it is the right function in a certain sense. And that is because when C is 1, when the capacity of each bin is 1, then we will have that a fraction of an epsilon fraction of the bins are empty. So even when inserting the ball, if we each time we're allowed to pick a bin uniformly at random until we found a non-full one, we would still expect to visit order 1 over epsilon bins before finding a non-empty one. So I'll get back to this result in a moment. First, I want to say that this consistent hashing with bounded loads has actually been adopted by both Google Cloud and also by Vimeo for their video streaming services. And this figure is from a Vimeo blog showing the bandwidth before and after implementing this solution. And as you can see, it has quite a significant effect. So let's talk about our algorithm. And the idea is essentially to combine the bounded loads with the use of virtual bins, the two solutions we just discussed. So our solution uses k levels, and each bin has a virtual bin at each level. So this blue bin would have a virtual bin at each level. This green bin would have a virtual bin at each level, and so forth. And now the balls a ball is not hashed to all of the level. A ball is just hashed to a single random level, in contrast to the bins. So the placement of the balls could look something like this. And now to describe how the balls are actually placed in the bins, we start from the leftmost level, and there we just place the balls using normal consistent hashing with bounded loads. So the red ball gets forwarded to the blue virtual bin and gets placed in the blue bin. And the blue ball does the same, and the purple one gets into the green virtual bin and gets placed in the green bin. Now we proceed to the next level, and we essentially just do the same, placing the balls from the next level using consistent hashing with bounded loads, except that now some of the bins have actually had some of their capacities reduced. So we would do the same, and in this case, the brown ball would go in the blue bin, and the green ball would go in the orange bin, which both have capacity enough. But then on the final level, something more interesting happened, and that is the pink ball gets forwarded to the blue virtual bin, which is full, and then we have to continue forwarding it on that level to this orange virtual bin where it gets placed. And for the gray ball, it would get in the green bin and virtual bin, and that bin is actually not full. So I'll get back to in a moment some more details about this data structure, but let me start out by talking a bit about its flexibility, or two parameters you can adjust. And the first one is the number of levels. We can choose the number of virtual bins, k per bin, but we can also make the hashing of the balls to the different levels non-uniform. So you could have that the probability of hashing to level I is 1/k for each level. And then you would have essentially more or less the same number of balls hashing to each level. But you could also imagine some other probability distribution where, for example, it became less and less likely to hash to higher levels. And we will in fact use these skew distributions in our results. So let me talk a bit more about how searches and insertions are performed. And as we discussed before, the static image of placement of the balls into the bins is found by placing the balls in hashing to the first level using normal consistent hashing, the balls hashing to the second level using normal consistent hashing with bounded loads, and but this time with reduced capacities and so forth. And now suppose we want to search for this green ball, which is not in the system. So what we do is that we hash it to one of the cycles, and we check out the first virtual bin. And looking in bin number 1, we see that it is full. And not only is it full, it also is filled by balls hashing to this level and levels below. And this means that we have to continue walking along the cycle. We go to the virtual bin number 2, and we see the same thing. But now when we get to bin number 5, we see that bin number 5 is full, but it got full, including some balls landing in later levels. And then we can conclude that this green ball is not in the system, because if it were, it would have kicked out some of these pink balls. So that's a search. Let's say that we want to insert this green ball instead. And if we do the same thing, hashing it to the cycle and going through bin number 1 and bin number 2. But then when we get to bin number 5, we actually kick out one of these pink balls because hashing to a later level. And now this pink ball has to be reinserted at a later level. And that is done in the same way, forwarding it clockwise around the cycle until we get to bin number 3, virtual bin number 3, which is in fact non-full. And again, it turns out that it suffices to analyze insertions of balls, because deletions of balls and insertions and deletions of bins actually follows from the bounds on insertions. And let us start by talking about the best case, what bounds we ideally could get, what bounds we could hope for. And let's say we are we are going to insert a ball into a bin. Then ideally, when placing the ball, we would keep picking uniformly random bins until we found one which is one non-full, where we would place the ball. And the point is that with capacity C, which is 1 plus epsilon times more than the average, at least an epsilon fraction of the bins are going to be non-full. And that means that we expect to visit order 1 over epsilon bins for this until we find a non-full one. Now, looking back at the consistent hashing with bounded loads, that gave the bound of order 1 over epsilon squared. And that's because, like in a solution like this, there's a certain cascading of balls, meaning that once you arrive at a full bin, it becomes more likely that the next bin will also be full. So I guess this is a good point that this is our first result, that we can actually achieve this ideal bound of order 1 over epsilon. And we do it using log 1 over epsilon levels, where the hashing to the levels is non-uniform. So essentially the probability of hashing to level I is 2 to the minus I. Yeah, so the probabilities would look something like this. So we do obtain this ideal bound of 1 over epsilon, and it's important to remark that if we just kept inserting into uniformly random non-full bins, we couldn't maintain all of these ball and bin insertions and deletions, but with our data structure, we can. And this is optimal when C is, in this sense, is a constant, because no matter how the balls are placed, at most, an epsilon fraction of the bins will be empty or non-full. So this leads to the natural questions about what happens when C is larger than 1, larger than a constant. Because when C is larger than a constant, we expect fewer bins to be we expect more bins to be non-full, and it was the number of non-full bins that determined the complexity in the previous result. And this is what led us to study this much simpler problem, where we distribute n balls into m bins, each of capacity C. And for each ball, we keep picking a uniformly random non-full bin, and we want to know what is the fraction of non-full bins. And to our surprise, this problem turns out to not have been studied before, even though that's a bit remarkable, given that it's quite a simple problem, just distributing balls at random into bins with capacitors. And it turns out that if you define this rather complicated function of epsilon and C, then we can prove that in expectation and with high probability, the number of non-full bins is going to be theta of f. And when we keep picking a uniformly random bin with f non-full bins, we then expect to visit order 1 over f of them before we find one that is non-full. And it turns out that we can actually achieve a similar bound with our data structure if we use enough levels. So we show, and that is our main result, that using order 1 over epsilon squared uniform levels, we expect to visit order 1 over f bins during an insertion. And again, it's important to remark that our setting is much more complicated, and we can actually handle ball and bin insertions and deletions dynamically, in contrast to this much simpler problem. So let me talk a bit about how we get to this main result. And let me start out by talking about this simpler problem where we keep picking a uniformly random bin for each ball, a uniformly random non-full bin for each ball. And we ask, what is the fraction of non-full bins? And the way we analyze it is by taking an alternative viewpoint. So instead of choosing a uniformly random non-full bin each time, we just choose a uniformly random bin, meaning that some of the bins may end up getting overfull. And what we do is that we just don't count these red balls. So we stop as soon as the number of green balls in the system is n. And if we let n denote the total number of balls placed so far, then it's rather easy to show that n is concentrated around some unknown mean n star. And then the way we can analyze this simpler problem is just by placing n star balls, capital N star balls into m bins. And the number of balls in a bin is then going to have this binomial distribution. And using the fact that we know that we stop when we have placed n green balls, we can actually determine n star. And once we have n star, we can also use estimates on the binomial distribution to determine what the probability is that a bin is non-full. So that's the first step, and that's what leads to this rather complicated function from the previous slide. And then we have to understand what happens in our more complicated setting with our algorithm. And in the problem is that we don't have this nice binomial distribution any longer. In fact, the number of balls landing in a bin at a given, in a virtual bin at a given level, follows something that looks more like a geometric distribution. So essentially, the number of balls landing in a given bin becomes a sum of geometric random variables with different parameters, essentially. So what we have to do is analyze, make the analysis from the simpler problem also work in this more complicated setting, and it turns out that we can in fact do this, and again obtain that the fraction of non-full bins is going to be asymptotically f, this formula. And now the final step of the analysis is analyzing an actual insertion. Recall that we did the insertion by hashing the ball and going through virtual bins at a level and sometimes jumping levels. But the important thing is that as soon as we arrive at a bin which did not get full from any level, then we can insert the ball. And what we show is that, in fact, in each step, the probability of being done is going to be theta of f. And the high-level idea behind this is that when we arrive at a virtual bin at a given level, this bin is still a uniformly random bin from the perspective of the other levels. And since there are a fraction of f non-full bins, essentially we get that with probability f, this given bin will be not too close to being full. And then secondly, because we have enough levels, the contribution from the given level is going to be small. It's likely to be small. And then these two things combine to actually give the bound of f. So of course, there are a lot more details to this analysis. We can mention that one of the technical challenges, and which took us a long time to overcome, was to resist the temptation to look at the insertion taking place on each of the levels and then using linearity of expectation to sum over all the levels, because that doesn't work, and it's just a very tempting natural analysis. But it turned out that we had to do this different analysis below. So that's just one of the technical challenges, and that's all I wanted to say. So I hope you enjoyed the talk, and thank you so much.